And next we'll have Michael telling us about handling scope checks. Yeah, please start.
Hi, I'm Michael, and I'm going to be telling you about handling scope checks. So this is joint work with Ningning, Oleg, and Jeremy. I'm going to start by setting the scene. So this work is grounded in the context of MetaOCaml, which is a project that aims to add compile-time metaprogramming to OCaml. When you're adding metaprogramming to a system with effects, like OCaml has, you have to be worried about scope extrusion. I've put up the definition here. It's the unintended and undesirable consequence of the interaction between metaprogramming and effects, but we'll see concrete examples of that later. I don't expect you to understand what it is right off the bat. There are various ways of solving scope extrusion. It's a well-studied problem. And the first two of these, refined environment classifiers and closed types, they are static prevention techniques, and the last of these, the MetaOCaml check. So MetaOCaml is a runtime metaprogramming system for OCaml that's a dynamic check. And we knew that we wanted a dynamic check because we didn't want to mess around with the OCaml type system. And we could have picked this and just taken it off the shelf, and that would have been fine, I guess. But instead, I had to ask a question. And the question I asked was, what's a dynamic scope extrusion check? And are there different types of dynamic checks? And are there trade-offs between these different checks? Do different checks even solve the same problem? And are these checks designed with effect handlers in mind, or just, state and exceptions? And asking these questions led to some answers. For example, we developed a theoretical framework for scope extrusion, which has typed effect handlers at both compile and runtime. We use this framework to facilitate comparison of different types of scope extrusion checks. Turns out that they don't all solve the same problem. They're similar but different, and we make that precise. They also didn't accommodate effect handlers, so we designed a scope extrusion check that did. And we showed that they can work well with static type systems, even though that's not our main focus. These are the contributions to the paper. Before you get your bingo cards out, I'm not going to be talking about all of these. Instead, I'm going to be focusing on just 3 of these. But before I asked any of these questions, I had a much simpler question to contend with, which is, what's metaprogramming? And that's not a question I have time to answer today, but I'm going to ask a different question, which is, what's MetaOCaml style metaprogramming? And for those of you who are familiar with the literature, this is 2-stage, homogeneous, compile-time metaprogramming, and that question I can answer today. So metaprogramming is the act of writing code that writes code, and if you've ever written a C macro, or a C++ template, or a Rust macro, you've done some metaprogramming. Our model for metaprogramming is programs that build ASTs. So here's a language in which you can do metaprogramming, or here's the syntax of a language in which you can do metaprogramming. We're going to assume it has the sort of obvious semantics. And it's important to note that this model of metaprogramming as AST building isn't new. So that's a paper you can look at if you're interested. You can also read off the programming language in which we generate code. The programming language of the code we generate just by looking at the ASTs. It's also a slight simplification of the language that we present in the paper. We also have a formal parameter constructor. So what we mean by this is that the AST of the identity function looks like that, rather than lambda, var alpha. It's just to keep things, it's just to keep the type system simple. We don't really have to worry about it. But here's our programming language in which we can do metaprogramming or AST building. So we've got our programming language. We can write some programs. We can write, for example, the AST of the identity function. Or we can write a program that actually computes, that does some computation. So this is a function application. On the left-hand side, we have a function that takes an argument and constructs the AST of that argument plus 0 that we apply to the AST of 1. So we can run it and get the AST of 1 plus 0. And this is sort of what happens at compile time. So compile time evaluation produces compile time normal forms, and these compile time normal forms are ASTs of runtime terms. They're ASTs of runtime terms, so we can move it into the runtime world where it's 1 plus 0. We can run it, and we can get 1. And that's just the regular runtime evaluation that you're familiar with. So that forms our model. We start off with a compile time term, which manipulates ASTs. We run it to get the AST of a runtime term. We then bring it into the runtime world and run it again, and then we get our runtime normal form. So that's our language in which we can do AST building, but it's sort of a difficult language to program in, and it's also a difficult language to specify because we've got lots of duplication. So we're going to add some syntactic sugar. And to add a syntactic sugar, what we're going to notice is a correspondence between the compile time terms and the runtime terms. So for example, we've got variables at compile time, and the ASTs are runtime variables, same for lambdas, and same for application. So instead of having all of this duplication, we're just going to introduce some shorthand, and that shorthand is going to let us convert between the two sort of coupled forms. And that shorthand is a quotation, which is the double angle brackets, and a splice, which is the $. And what quotation means is it says interpret the expression as an AST, and what the splice means is don't interpret this expression as an AST. And importantly, we start by interpreting things in AST mode because we model compile-time metaprogramming, and this lets us write normal programs without any metaprogramming. So this was the example that we had earlier. We can write it in the code splice form, and what we say is that the code splice form means the AST form. Formally, we define an elaboration from the code splice form into the AST form, and I'm going to show you what that elaboration is now by walking you through the elaboration of this particular code splice program. So we're going to start off with a top-level splice. That's a splice not surrounded by any quotes, and the reason why we have that is because, once again, we start in AST mode. And starting in AST mode is sort of equivalent to having these ghost brackets around everything. So we start by converting things to AST. The splice tells us to stop, which means we interpret the application as just a regular application rather than the AST of an application. Then we convert the function. We see the quotation, so we need to convert the plus into the AST of a plus, and then convert the left and right-hand sides. When we convert the left-hand side, we see the splice that tells us don't convert the x. This just gets converted to the AST of a 0, and this gets converted to the AST of the 1. And then we get our original program back. So this completes the model. We had compile-time evaluation and runtime evaluation, but we have an initial step, which is elaboration from a code splice language to a language with ASTs. And we're going to give these languages names, so I don't have to keep referring to it as the code splice language. We're going to call it lambda code and lambda AST. We're going to say that lambda code has expressions and lambda AST has terms. I think in the paper we've got lambda code op and lambda AST op because by this point I've introduced effects. But that's just something to keep in mind. So that's our initial model of metaprogramming. But I didn't say that MetaOCaml was about metaprogramming. I said MetaOCaml was about typed metaprogramming. So we need to add types. Let's start by adding types to lambda code. And in lambda code, what's interesting is that we've got compile time types and runtime types. For example, we can have naturals at compile time, and we can have naturals at runtime, and the two shouldn't be able to interact. You can't add a compile time natural to a compile time to a runtime natural, for example. So to distinguish between the two, we're going to add these things called level annotations: -1 for compile time and 0 for runtime, and that just makes sure that we keep them separate. Similarly, we enforce a separation between compile time functions and runtime functions, but this is a very complete separation, and in order to do metaprogramming, the stuff at compile time needs to somehow manipulate the stuff at runtime, the ASTs of the stuff at runtime. So in order to do that, we expose an image of the runtime types in compile time, and to do that, we have a compile time type constructor, the code type constructor. So for example, we can convert runtime functions into the compile time code of runtime functions. And what quotation and splice do at this level is that they simply convert between the sibling coupled forms. So that's the type system for lambda code. We also add a type system for lambda AST. It's a lot simpler. We just add an AST type constructor for the AST forms. We had an elaboration from lambda code into lambda AST terms. We are going to do a similar elaboration for types. Remember that lambda AST is designed to be run at compile time, which means that compile time naturals just become regular naturals. Compile time functions become regular functions, and runtime naturals and the code of runtime naturals become the ASTs of naturals. So now we've got our languages and we've got our type system. We can ask, what's the type preservation theorem? And the type preservation theorem has the same shape it always does, which is that well-typed terms don't get stuck. And importantly, they don't get stuck at any point in the process: elaboration, compile time evaluation, or runtime evaluation. So how do we prove this? Well, first of all, can we prove this? And second, if so, what can we rely on? Well, first of all, we have that well-typed terms don't get stuck at elaboration. So well-typed lambda code expressions elaborate into well-typed lambda AST terms. This is something that we prove in the paper. We have that well-typed lambda AST terms don't get stuck. This is kind of easy to prove. And we have that our runtime language, which is just a lambda calculus with arithmetic, doesn't get stuck, which is fine. But that's all we need. We need an additional lemma, and that lemma is that the lambda AST normal forms are ASTs of well-typed runtime terms, because we need to know that we've got a well-typed runtime term. And that's not what I said earlier. I said that lambda AST forms are ASTs of runtime terms. And there's a reason why I said that, and the reason is effects. And rather than giving you our formal account of effects straight away, I'm just going to add exceptions, and we're going to see how even exceptions cause a problem. So once again, so this is a program that causes an error. We start once again with a top-level splice that just tells us to interpret it as a regular program. We install an exception handler, and we try and construct the AST of a lambda. That is the AST of the lambda. We're going to try and construct the body now. I'm going to skip a few steps, but basically how we're going to try and construct the body is we're going to first raise an exception and then return the variable. So that's how the elaboration works. Now we can try and run this lambda AST program. When we try and run it, we're going to raise the exception. The payload var x is going to get bound to z, which we're then simply going to return, and the entire program is going to step to the AST of x, which is of course not well-typed because x is free. So well-typed programs do get stuck. And this is scope extrusion, right? This is the interaction of metaprogramming with effects. It's actually a very specific type of scope extrusion, which we call lazy scope extrusion, but I'll get into that distinction later. Although this example is caused by exceptions, scope extrusion can be caused by a whole host of effects. So that's scope extrusion. How do we solve scope extrusion? And one potential approach is to change the type system for lambda quote and lambda AST so that scope extrusion programs aren't ill-typed. We call this approach static prevention, and it's well studied in theory, which is great, but it tends to limit how effects can be used. And as I've said earlier, it requires wrangling with the OCaml type checker, which I really didn't want to do. So that's not what we're going to do. Instead, we're going to ask, can we check for scope extrusion and raise compile time errors when we run the lambda AST program? And this approach, which we call dynamic checking, isn't that well studied in theory, but empirically it tends to allow more flexible use of effects, and it didn't require me to modify the type checker. So that's what we're going to do. If you're curious, there are approaches that modify the type checker. I think contextual squid's a good example of that. So now we're going to study dynamic scope extrusion checks in theory, and we're going to start by asking the question, what is a dynamic scope extrusion check? And the key insight is that here we're using an elaboration to give a meaning to quotation and splice. And currently, the lambda quote program means something that runs to something that when it terminates returns a free variable, or the AST of a free variable. But that's not actually what we want it to mean. What we want it to mean is something that raises an exception at runtime, at compile time. So we need to change the meaning of the quotation and splicing, which means we need to change the elaboration, and we need to change the elaboration in such a way that it inserts checks, and these checks can raise exceptions. So that's what a dynamic scope extrusion is. A check is in our model. It's just an elaboration that inserts checks. So a very natural question to ask is, how should we insert checks? And different answers lead to different types of dynamic scope extrusion checks. The first option is to evaluate all the way until the end and then perform checking. We call this the lazy check. So let's see how it works. We start off with a lambda code expression that we elaborate into a lambda AST term, which we can then run until completion. At the very end, we check the normal form that we get to make sure that it doesn't have free variables. This is a really simple approach, and it's really good in some ways. We say it's correct and it's maximally expressive. These are technical terms that, if you're familiar with static analysis, correspond to soundness and completeness. But there is one problem with the lazy check, and that is it's horrible to use in practice. And the reason why it's horrible to use in practice is because you have to wait until the very end. And because you wait until the very end, you lose a lot of information. There are no stack traces. You have to wait for the entire program to compile before an error is reported, and I guess that's fine if you want to go drink a coffee rather than do work. And also variables can be bound in really nasty ways. And I don't go into this in the presentation or in the paper, but we do point to research that talks about this. And you don't have to take it from us. This is what Offenbeck and all say when they use the lazy check to build the RAND-IR system. They say that errors are reported in very obfuscated ways, precisely because you're waiting until the very end. So the lazy check isn't great. Another option, therefore, is to check whenever an AST is built. And this is the check. We call this the eager check, and it's what's used in MetaOCaml. So let's be a little bit precise about what it means to build an AST. Here's a program where we build the AST of 2, bind it to x, and then return x. When we return x, that's not building another AST, that's simply returning a pre-built AST. I hope that gives you a sense of what it means to build an AST. We can look at the trace under the eager check, and importantly, we're not just going to check at the very end, but we're going to check at various points along the way whenever an AST is built. I think it's important to take a step back here and realize that the eager check uses a different definition of scope extrusion than the lazy check. So for the eager check, a free variable in T2 is bad and will cause scope extrusion that will be reported. But it might not cause scope extrusion under the lazy check, because the lazy check is a free variable at the very end, and maybe that free variable won't appear. So lazy scope extrusion checks for free variables after code generation, after the entire process, right? Once you have your normal form. Whereas eager check checks along the way. So obviously these are different definitions, but we can ask, do they coincide? Do they happen to be the same? And returning to our example, we can ask, must the free variable in this case, T2, show up free in the normal form? And here I'm assuming that compile time generation terminates. Well, no. First of all, that free variable could be thrown away. But second, perhaps it could appear, but appears bound somehow. That first problem isn't really a problem, because if you throw it away, well, I don't really mind reporting an error there. But that second problem, let's investigate whether or not free variables can appear bound in the end result of program generation. And in order to ask that question, we need to ask a different question, which is, can we capture a continuation containing a binder and reinstate it? Because if you can, then we can take free variables and make them bound again. And the answer to this is slightly complex. Not technically complex, but historically complex. The answer is that it wasn't common when the eager check was introduced in 2014. And in fact, this is what Oleg says. The ability to re-enter scope, dynamic scope was uncommon at the time. If you can, well, it results in false alarm. That was in 2014. In 2022, effect handlers were added to OCaml. And effect handlers give us precisely the ability to restore safety once we enter scope extrusion. So, brief tour of effect handlers. Here's a program that raises an exception R with a payload 0 and then returns 0. We're going to ask, can we handle the exception R by going back to the point where it was raised and replaying it with a value of our choice? This is an operational account of effect handlers, and that's really the only account that we need. So we need a definition of what that point is, the point where the exception was raised. And we define that point as a continuation. That's the stuff that would have been done at that point if the exception had not been raised. In this case, we're just adding 1 to the result. And we're going to bind it to K, the continuation. We're going to introduce a new keyword, continue, that lets us go back into the hole and plug it with the value of our choosing. That lets us go back to the point the exception was raised and resume. And here I'm choosing to resume with 0, but I could have chosen to resume with another number like 3. Some syntactic differences between effects and exceptions. We use handle instead of try and perform instead of raise. That's what effect handlers are, and what they do in our case is that they give us the power to recover from scope extrusion. Here's an example of a lambda AST program where we perform an effect. When we perform an effect, we take the payload var x and we bind it to z, which we then substitute into the plus z0 expression. So we get the AST plus var x 0. And this, note, var x is not bound in the AST in this case, so this is eager scope extrusion. But we also generated a continuation, and that continuation has a binder for x. And in fact, we use the continue keyword to plug that malformed AST back into a scope in which it's saved. And so the free variable that would have caused eager scope extrusion appears bound in the final term and does not cause lazy scope extrusion. So, resuming continuations can restore safety after eager scope extrusion has occurred, causing exactly the false positives that Oleg talked about. That's a problem, but in our opinion, that's not the biggest problem. To see the biggest problem, we're going to translate this lambda AST program into its lambda code equivalent, and we're going to call it B. And here I'm going to act like an optometrist, because I'm going to ask you, do you think there's a difference between B or A, or do they look the same? And the important difference to note is that B has that plus 0 and A doesn't. And the question that we're going to ask is, so we know that B fails the eager check and is a false positive. Is A also a false positive? And the answer, somewhat unintuitively, is no, it's not. And the reason why is because that plus 0 builds an AST, and that doesn't. That returns a pre-built AST, which is really unintuitive until you expand it out. So we didn't like that, and we wanted to design a check that lets B pass as well as A. So neither B or A would be false positives. And that's our novel check. And what we do is we check at different points. What we do is we wait until all continuations are gone, and then we check eagerly. And we call this the cause for concern check. So we can look at how it looks like operationally. What we do is we change each check into something called a check M. A check M is like a smart check. It's aware of continuations that are still on the stack, and if it sees any, it erases itself. And so consequently, in the earlier example, we can not report an error in B, so it doesn't become a false positive, because we see K, and we know that it's still around, and we know you could use it to restore safety. So the C4C check uses its own definition of scope extrusion. Like the eager scope extrusion, is defined in terms of intermediate states, because you want to report scope extrusion early. But unlike eager scope extrusion, it's not just a free variable in an intermediate state, but it's a free variable that must be free at the end result of evaluation. So that simulates the lazy check, or that has the same idea as the lazy check. And so that characterizes our goal. We want to catch lazy scope extrusion, not eager scope extrusion, but we just want to do it earlier. So our C4C check is correct, but it's not, unfortunately, maximally expressive. And this is a program that causes it to not be maximally expressive. This is a false positive. I don't really need you to know what it does, but after elaboration and evaluation, we get this. And what's important to note is that we build an AST with a free variable, y, and at that point, there are no continuations left on the stack, so the C4C check will fail here. And this shouldn't be surprising, because earlier I said that there were two ways, and if we had continued, sorry, the malformed AST would have been thrown away, and we would have returned the well-formed AST of 0. And this shouldn't be surprising, because earlier I said that there were two ways in which scope extrusion at intermediate points might not show up at the end result. First of all, you can rebind continuations. You can use continuations to rebind free variables, and second, you can throw unbound variables away, and I only solved the first one. Here, we're still throwing unbound variables away. But all false positives look like this, and we formalize this in a cause for concern property that states that if our cause for concern check reports an error, the only thing you can do with that AST, the only valid thing you can do with that AST to restore safety is to throw it away. So I don't mind reporting a false positive in that case. That's basically it for the presentation. There's a lot more in the paper that I didn't have time to talk about today. There's also an artifact and an implementation of the C4C check in MetaOCaml, where we empirically validate the claims of this presentation and the paper. But in this presentation, I've introduced a theoretical framework for studying dynamic scope extrusion checks. I've used it to encode, compare, and evaluate existing dynamic checks. And I've introduced our novel C4C check that is designed with effect handlers in mind. Thanks very much.
Are there any questions for Michael? So hard to see.
Thank you for a great talk. Yeah. So my question is very simple. Well, you stick to compile-time metaprogramming, well, but many ideas came from MetaOCaml or Oleg. Does your result hold for also for runtime metaprogramming?
Yes, so that's a great question. I believe it does. Compile-time metaprogramming and runtime metaprogramming look very similar at first, but they're actually quite different. However, I think in our calculus happens to operate in the exact subset in which they coincide. So I think our approach extends to runtime metaprogramming. There are practical trade-offs. For example, although ours is a dynamic check, our errors are still reported at compile time because it's of compile-time metaprogramming. But in terms of, I think the properties that we have, it should extend that quite naturally.
We've got time. Question in the middle. If someone can get a microphone there.
Thanks for the talk. I also have quite a simple question. Here, scope extrusions, so you need to check for them because you have effects kind of in the object language. But if you only have effects in the meta language and not in the object language, you don't need scope extrusion checks. Am I right?
Right. So scope extrusion occurs if you have effects in the meta language. That's the compile-time language, the language that performs the code generation. So if you only have effects in the runtime language, so if you only have effects in if you only have the ASTs of effects and not effects themselves, then you're fine. That's correct. So if your compile-time language is pure, and that's a completely valid approach. So you prevent scope extrusion by saying everything you can do at compile time is pure. But we wanted effects at compile time because when you have effects in your meta language, in the language that does code generation, you tend to be able, it's a lot easier to implement certain optimizations like loop invariant code motion because you can lift things outside particular scopes, right? If you lift them too far, then it becomes scope extrusion, but you can lift them just a little bit and then you get things like loop invariant code motion.
Thanks.
I think we'll move on to the next talk now, so could we thank the speaker?